4b, Kinematics Describing Motion. 4.6, Introduction. Kinematics does not deal with the properties of moving objects themselves, only with the way they move. Kinematics measures the positions, speed or velocity, and acceleration of objects. As Galileo believed, it is necessary for a scientist to describe how things move before he can explain the causes of their motion. 4.7. What is motion? Motion occurs when a system's position changes during an interval of time. Depending on the number of coordinate axes in one's frame of reference, a system may require 1, 2, or 3 coordinates to identify its position. For one-dimensional motion, only a single position coordinate is needed to identify a system's position, symbolized as x. Subscript numbers are used to indicate a sequence of positions over time, for example, x1, x2, and so on. If only the initial and final positions are important, you can use the symbols xi and xf, respectively. 4.8 Distance and Displacement. Imagine that just before dinner, you're reading a book in your living room. Your mother calls you to set the table for supper. You walk to the kitchen, make several trips between the table and the kitchen, carrying utensils, food, and condiments, and then sit down at the table. What was the total distance you walked between your living room seat and taking your place at the table? If you measured the length of every step between the chair, the kitchen, and the table for every trip you made and added up the individual lengths, you could arrive at the total distance you traveled. Distance is a positive scalar quantity because there is no direction associated with it. Thus, for example, you would report the total distance walked as 20 meter. Now, what was your overall change in position between your living room seat and the table? In most cases, this is a very different quantity from the distance you traveled. The change in position involves a distance, to be sure, but it also includes a direction. What kind of quantity is this? It is a vector quantity physicists call displacement. The distance part of your displacement vector is the shortest distance between the couch in the living room and the chair at the table. The direction portion of the vector from the living room to the table could be measured relative to some directional reference, like geographic north. The complete displacement vector might be stated as 3.4 minute northeast, for example. Notice that 2 pieces of information are required to completely describe a vector size, a scalar value, and direction. To simplify the analysis of this example, you could choose a coordinate axis that lies on a line connecting your living room couch and your seat at the table. You could place the origin at the couch. Then, your displacement would simply be the distance between the 2 seats in the direction of the table. See Figure 4 to 13. The distance in this case is the magnitude of the displacement vector, or just its length. The magnitude of a number or vector is its absolute value and is always positive. The magnitude of a displacement vector and the distance traveled are equal only when the object has traveled a straight line in one direction between the beginning and ending points. This is always true of one-dimensional motion. 4.9 Speed and Velocity. A honeybee, Apis mellifera, may fly 1 meters in 0.1 s, while a glacier may take a year to move the same distance. They've moved an equal distance, but the motion occurred over very different time intervals. How fast motion occurred is the quantity speed. The speed of a system is simply the rate of motion. A rate compares the change in the value of a quantity to a certain span of time. Mathematically, speed is equal to the distance traveled in an interval of time, divided by the time interval. In a formula, speed is written as speed, v, Shakespeare distance over time interval, Shakespeare d over delta t, v equal d over delta t. Since distance and time are always positive, speed is too. You don't concern yourself with the direction of motion because speed is a scalar quantity. The average speed, v average, of a system during an interval is equal to the total distance traveled divided by the time interval. In the real world, the actual speed at any moment, called instantaneous speed, is probably lower or higher than the average speed of the system for the entire interval. For example, the speed indicated on a car's speedometer is instantaneous speed. When you calculate your speed from the total distance of your trip and the time it took, you're calculating average speed. Average speed is the constant speed you would have to travel with no slowing down or speeding up to make the trip in the same time interval. When both speed and direction are important, you use velocity. Velocity is the rate of completing a displacement. Since displacement is a vector quantity, velocity is also a vector. You calculate the average velocity of a system by dividing its displacement by the displacement's time interval. Velocity, v. Shared displacement over time. Interval, shared d over delta. T, v conjugate d over delta t. The bold characters stand for vector quantities that might point in any of three dimensions. Since you will be studying only one-dimensional straight-line motion in this course, we will use the scalar symbols in these formulas to keep them simple. As long as the system's direction of motion doesn't change during a time interval, distance and displacement will be identical. In a simple description of one-dimensional motion, you can use a plus or to designate the direction of the velocity vector. For instance, consider a hybrid energy car traveling east at 30 mph and a hydrogen fuel cell car traveling west at 45 mph. The velocity of the eastbound car is v sarc plus 130 mph, and the velocity of the westbound car is v cha 45 mph. The selection of which direction to label positive is completely arbitrary, but the sign of the opposite direction must be negative. Physicists find velocity much more meaningful than speed for calculating momentum, centripetal force, and torque, as well as other quantities. Several of these are discussed in other chapters. Calculations involving speed and velocity. Optional. The formulas for finding speed and velocity contain three variable quantities: distance or displacement, time interval, and speed or velocity. Such formulas are useful because knowing any two quantities enables you to find the third. The formulas can be rearranged using simple algebra. The following example problems illustrate just a few real-world applications. 4.10. A cceleration. When a speed skater hears the starting gun, he changes his speed from 0 to a high value in a short amount of time. The change of his speed is his acceleration. Acceleration is the rate of change of the speed or velocity during a given time interval. Note that acceleration may apply to a change in a scalar or a vector, so acceleration may itself be either a scalar or a vector. To calculate average acceleration involving a change of speed, subtract the initial speed from the final speed, and then divide by the time interval of the speed change. Average acceleration, AE average, just change in speed over time interval, just delta V over delta, T. AE average, shared VF VII over delta T. The formula used for calculating acceleration in which velocity changes is similar to this formula, except that velocities are substituted for speeds. This difference is important. Remember that the speed is simply the rate of change of position. Direction is not considered. With velocity, both speed and direction must be considered. Therefore, a change in velocity might involve a change in the speed, a change in direction, or both. An acceleration occurs in any of these three circumstances. For this course, you will solve problems involving only one-dimensional speed changes. Just be aware that acceleration includes changes in both speed and direction. There are several things to note in the above example. First, the car is traveling in one dimension. Second, when substituting velocities into the formula, parentheses are used to keep the signs of the velocities separate from the subtraction operation sign. Also, observe that the sign of the acceleration is positive. This means that a velocity is increasing during the time interval in the positive direction of the coordinate system, north. Finally, the units of acceleration are meters per second, MSS. This expression is usually shortened to meters per second squared. This problem illustrates something important about vectors. That's a negative vector points in the direction opposite the positive direction of the coordinate axis. In the above example, the acceleration vector is pointing west, even though the velocity of the car was toward the east. In a one-dimensional coordinate system, Negative acceleration or deceleration acts to slow, stop, or reverse the original positive velocity. Negative acceleration can also increase velocity in the negative direction. 4.11 Motion in 2 and 3 dimensions. Although your study of motion in this course concerns mainly one dimension, most real motion occurs in 2 or 3 dimensions. Therefore, you should be familiar with 2 and 3-dimensional motion. Motion in 2 dimensions involves changes of position on a coordinate plane. 2-dimensional motion may occur in a horizontal plane. For example, players on soccer field, cars on the road, or ships on the surface of the ocean move essentially in 2 dimensions. It may also occur in a vertical plane. For example, the path of a thrown ball or a falling aerial bomb lies in a vertical plane. Position in a plane is determined using 2 coordinate axes perpendicular to each other. The origin is located where the axes intersect. Each position in the system must be described by 2 coordinates, e.g., x and y. 3-dimensional motion occurs in all 3 spatial dimensions: length, width, and height. Roller coasters, acrobatic aircraft, thunderstorm thermal updrafts, and geologic fault motion are examples of motion in 3 dimensions. Position in 3 dimensions requires reference to 3 mutually perpendicular coordinate axes. Their common intersection is the origin for the spatial reference system. Positions are described by 3 coordinates, e.g. x, y, and 2. The definitions of distance, displacement, speed, velocity, and acceleration are the same in 2 and 3-dimensional motion as they are in 1-dimensional motion. Calculating their values can be more complicated because you must understand a kind of geometric math called trigonometry. You will have an opportunity to study 2 and 3-dimensional motion in more advanced courses in physics. 4.12 Using kinematics to solve problems. In a car accident, 2 collisions take place. The car decelerates as it collides with something, and the occupants decelerate when they collide with the interior of the car or when something restrains them. Car accident decelerations take place quite rapidly, causing injuries. As the acceleration equation in subsection 4.10 predicts, if the same change in speed happens over a longer time interval, then the rate of acceleration decreases. Padding and restraint systems used in car seats increase the likelihood that a child will survive a car accident by increasing the time interval for the same change in speed. According to studies by the Washington School of Medicine, car seats drastically decrease the risk of death by 71% for infants and 55% for toddlers. This is why every state in the United States requires that small children travel in car seats. One of the child-sized crash test dummies recently developed for testing car seats and airbags goes by the acronym CRABBY. Using this dummy, scientists reconstruct the conditions of actual accidents that have resulted in child deaths to come up with possible solutions that will help keep children safe.